What's up guys, it's me Sir Ernest, and today we're going to solve problem 2.4 of Griffiths 4th edition. The problem reads, find the electric field at distance z above the center of a square loop, side A, carrying uniform line charge lambda shown in figure 2.8. Hint, use the result of example 2.2. Okay, so if you're going to recall that for a line charge of length 2L, so this is from example 2.2. Okay, and then let's say you have a point where the point is R away from the midpoint of this length. The resulting electric field at this point will be 1 over 4 pi epsilon naught times 2 lambda L over R times square root of R squared plus L squared. Okay, and the direction is away. So this is your electric field. Now we're going to use this result. Okay, we're going to look at the electric field contribution of each of the sides of the square loop. Okay, but please take note that this R will not be this Z, but instead the distance between our point will be this. So let's call this R. That means the electric field will be pointing somewhere here. Let's call, if this is let's say segment 1, let's call this E1. Now from here we can deduce or derive important equations or relationships. For example, R will now be equal to square root of Z squared. Because remember, this is a triangle, so this is Z squared plus this length is A over 2. So this is A over 2 squared. Okay. Okay. And then the L squared here, the L here. Okay, in this case, this one would be A over 2 as well. So this is L in this expression will be equal to A over 2. So that L squared will be A squared over 4. Okay. Now, so for one segment, okay, let's call that E1. Okay, if you're going to draw that, let's say this is your on this side. So this side will be this side, and then going looking towards you in this direction, this will be these two sides. Okay, so if this is your point P, this will be Z, and then this will be R. So E1 would be here. Okay, as you can see, by symmetry, the horizontal component of this electric field contributed by this segment will be cancelled by the other side. Okay, so that means the net electric field will just be the sum of the vertical components of the electric field due to each segment. So if we're going to look at here, this will be the vertical component of this electric field. Okay, so if the electric field using this one for this segment, that is equal to 1 over 4 pi epsilon naught times, okay, so this is 2 lambda L. L is A over 2, so this becomes lambda A. And then R will be Z squared plus A squared over 4. And take the square root. And then square root of R squared plus L squared. So this is square root of what? That would be square root of Z squared plus A squared over 4 plus A squared over 4, which is A squared over 2. Okay, so E1 vertical would be equal to E1 cosine theta. You know what is cosine theta? Cosine theta would be, if this is your theta, this is also theta. So that becomes Z over square root of Z squared plus A squared over 4. So combining everything together, this vertical component net would be 4 times EV1 because we have 4 sides. So this is equal to 4 E1 cosine theta, because remember this is also equal to E2V, same as E3V and E4V, where E2V, E3V, and E4V are the vertical components of the electric field due to the other 3 sides of the square. Okay, so this will now be equal to 4 over 4 pi epsilon naught times lambda A over this. So this is square root of Z squared plus A squared over 4 times square root of Z squared plus A squared over 4. Oh, so this becomes over 2. Because we could already combine these two. And then times cosine theta, which is Z over square root of Z squared plus A squared over 4, which can be combined with this. So therefore, the magnitude of the electric field, also the total electric field net, will be equal to 1 over pi epsilon times lambda AZ divided by Z squared plus A squared over 4 times the square root of Z squared plus A squared over 2 Z hat. Okay, that's it. That's the solution to problem 2.4 of Griffiths 4th edition. I hope you learned something today, and thank you for watching, and I'll see you guys in the next video. Bye bye.